Solvents are essential in chemistry, present during most experiments, yet explicit solvent behavior is not yet fully understood. With the AutoSolvate software package, I was able to run high-throughput explicit solvation for more than 100 systems. I observed that even for small molecules, most systems have multiple local minima. On the left, 3 local minima and 2 transition paths are visible. The investigated property also varies across this landscape. Some molecules, like ferrocene, have only 1 local minimum. Shown on the right, it still shows some changes in the investigated property. An accurate Boltzmann distribution is necessary for explicit solvation calculations, including sampling of slower transitions between local minima. Typically, solvent shells are investigated with radial distribution functions, but most systems are non-spherical, which can result in no solvent shells visible. I found that the minimum distance distribution function clearly shows multiple solvent shells from the same data. Here I define the solvent solute closeness as the minimum distance where the distribution function reaches above 1. I observed an almost linear dependency of the closeness on the solvent dielectric constant. This closeness is also highly predictable from the molecule structure. Hydroxyl and thiol functional groups reduce the closeness because of the hydrogen bonds. I also investigated the accuracy of the Marcus theory for explicit solvent. Is the assumption of linear response a good approximation? The reorganization energy, which is caused by the reorganization of the system and solvent conformations, allows to validate this linear response assumption. If true, then 2 different estimations of the reorganization energy, Stokes and variance, should be identical. I observed that up to statistical accuracy, this identity holds. Even less well understood is how much does the solvent contribute to the reorganization energy. Experiments generally show a large contribution, but I observe a small solvent contribution below 40% for the investigated small organic molecules. Another common question about explicit solvation is the size of the solvent shell necessary to converge the investigated property. A smaller solvent shell is desirable due to faster computation. For redox potentials when using microsolvate clusters, a solvent shell above 10 angstrom is necessary. This is reduced to only 4 angstrom with a combination of explicit and simultaneously implicit solvent, as shown on the bottom. I want to note that I measure the solvent shell thickness from the surface of the molecule to account for non-spherical systems. This investigation of explicit solvent behavior was done in collaboration and was published in these 2 papers.